Okay. Hi, everyone. I'm Dustin Lundmark. I'm the senior AE here at AdvancedTek. We're going to be going over getting the most from your FDM investment, trying to help select the right material for your application. Going over 4 categories today. General purpose. Usually their strengths are affordable, easy to print, versatile for everyday needs. Next is your engineering. Strengths are high toughness, fatigue resistance for repeated use. And your specialty category strengths are targeted performance for special or specific regulatory or functional needs. And your high performance extreme environment, its strengths are certified performance in extreme heat, chemical resistance, or flame FST. Your general purpose materials, you start off with your ABS M30, strong impact resistant with good layer bonding, reliable for everyday functional use. It's a great all-around material, ideal for functional prototypes, jigs, fixtures, manufacturing tooling. Next is your ASA material. It's a good UV stable with excellent weather and color resistance. Matches or exceeds ABS mechanical properties. Colors resist fading, and mechanical properties won't degrade over long-term exposure to UV light. Similar applications to ABS. Next is your PC ABS. Tough blend offering high impact strength, good process ability. Combines PC's superior strength, heat resistance, and flexibility of ABS. Deal for functional prototyping, tooling, and low volume manufacturing. Next is you get your PC, high toughness and better heat resistance than the ABS family. Strong parts that withstand functional testing, ideal for manufacturing, tooling, thermoforming, and production parts. Next is your PLA. It's easy, fast printing, sustainable. It's a non-toxic material that's made from renewable resources. Makes it good for educational settings. Has a relatively low cost and prints fast, making it great for early design concepts that can be printed quickly for design iteration. Next, you got your FDM HIPs. Mechanical properties are similar to ABS, but with much higher impact resistance. It's a good general purpose material for 3D printed parts needing greater durability than ABS. Excellent for low to moderate strength manufacturing aids that can be printed quickly. Next, you get your engineering materials. Starting off with your nylon 12. Has excellent toughness, fatigue resistance, and chemical resistance. Has high elongation at break, 5 times the elongation of other FDM materials. Excellent fatigue resistance, best impact strength. It's great for snap fit clip applications, and also great for tooling or prototypes with friction fit inserts. Next, you got your nylon 6. It's a higher strength and stiffness with good wear properties. Excellent strength and stiffness, good impact resistance. Nylon 6 combines the strength of Ultim 95 with the toughness of nylon. Overall, higher strength and stiffness compared to nylon 12, especially formulated for FDM printing. Next, you got your nylon 12 CF, CF10, and then your ABS CF10. It's a carbon fiber reinforced for superior stiffness and strength to weight. Your nylon 12, it's going to be a 35% fill by weight with chopped carbon fiber. It has the highest strength and stiffness to weight ratio. Good for manufacturing tooling that requires strong yet lightweight material that won't deform. And then your nylon 10 CF is obviously a 10% fill by weight chopped carbon fiber. It has very good stiffness and strength. And then your ABS CF10, that's also a 10% fill by weight, and then over 50% stiffer and 15% stronger than non-reinforced ABS. It also has a good low moisture sensitivity. Good applications include alignment tools, ergonomic aids, end of arm tools, and factory floor tooling. And then lastly, your Duran. It's a low friction, high impact, chemically resistant for robust tooling material. It's nylon-based thermoplastic, maintains a smooth, lubricious surface quality, great for jigs, fixtures, end of arm tools. Key tip when running this material is you want to dry it out, even when grabbing a brand new spool. That's helped me in the past when running this material. Next, you got your specialty materials. Starting off with your ABS ESD7. It's a static dissipative for electronics sensitive applications, or it's great for that. Ideal for jigs fixtures used to fabricate and assemble electronic components and associated production line items. Next, you get your ABS M30i. It's biocompatible for medical and food contact use. It has good impact, tensile strength, is gamma and ETO sterilizable. Good applications are medical handling, food handling, and pharmaceutical handling and tools. Next, you get your TPU 92A, flexible elastomer for seals, hoses, touch parts. Also, like the picture in the lower right, it's a good example of Indian Motorcycle using it for on their assembly line. They use it for locating jigs for stickers or decals. Obviously, TPU helps so it doesn't scratch the paint like a more rigid material would. I've also seen it used for pieces of electronic equipment protectors, essentially kind of like a phone case, to kind of help with the bumps and bangs that I would see during the day on an assembly line. The PA666 GF30FR, it's a glass-filled flame retardant material, great for the rail and transportation industries. It's a new material that just came out. It's a 30% glass-filled nylon. It meets the demanding industrial applications requiring high strength, stiffness, and fire performance. Next, you got your PCISO. It's a good high strength, impact resistant, and heat resistant material for industrial use. And then next, you got your Kimia PCFR, flame retardant polycarbonate with enhanced toughness. And then you got your PCESD, the sag dissipative polycarb for electronics protection. Next, you get your ST130. It's a soluble material used to make sacrificial 3D printed molds. So essentially, it's a support material used as a model material. It's good for composite material layup applications. Essentially, you wrap the ST130 in your composite or CF material, and then when it's cured, you tank it, and then you're left with your end composite part. Go over the key differences between the categories. So for your general purpose, its primary strengths are easy printing, good aesthetics, balanced properties. Limitations are lower heat chemical resistance than some of your higher level materials. It has a lower cost, which makes it good for prototypes, concept, non-critical parts where you're doing multiple iterations for form to function. Engineering materials has primary strengths are high toughness, fatigue and wear resistance, stiffness, especially the composite-based ones. Limitations are moderate heat, chemical performance, has a little bit higher cost than general purpose, and best suited for like tooling, jigs, repetitive use parts. Your specialty materials, primary strengths are ESD, flexible biocompatibility or flame retardant. Its performance can be narrow, and then a little bit about the same cost as the engineering grade materials, best suited for regulated or functional specific needs. And lastly, your high performance or extreme environment materials. Usually they offer superior heat, chemical resistance, FST rating, strength in harsh conditions. Limitations are it's a little bit higher cost and usually require some of the higher end printers like the F450 or F900. And then it's going to be one of the more costly materials. And then it's best suited for high demand areas like aerospace, oil and gas, or medical sterilization. Next, we're going to go over how material properties affect application performance. Properties like strength, stiffness, it's going to be critical for low bearing jigs, fixtures, structural and use parts. You'll probably want to go towards your engineering or high performance materials. Heat resistance usually determines suitability for high temp environments like under the hood or sterilization areas. Probably going to want to use your high performance materials. Chemical UV resistance, essential for outdoor use, fuel oil exposure, or like cleaning solutions. Probably want to go with your specialty or high performance materials. If you have any special needs like FST, ESD, or biocompatibility or regulatory must-haves in aerospace electronics for medical applications, you're probably going to want to go with your specialty materials. If toughness or fatigue ratings are critical, important for applications like repeated motion, vibration, or impact, engineering materials are a good one to go with. Or cost dependability, you'll have to balance cost dependability with performance and lifespan requirements. It all depends on the application, and that can range the whole range from general purpose up to high performance. Matching material categories to project type. So like a concept model, early prototype, probably want to go with the general purpose. It's fast, affordable, deal for visual models, fit checks, early design validation. So material examples are like your ABSM30, your ASA, and sometimes maybe even your PLA. Jig and fixtures, engineering or specialty materials are probably what you're going to go with, especially if you're dealing with electronics or ESD. Rating is critical. Prioritize durability, stiffness, wear resistance, and long service life. Some examples are like your nylon 12CF, your EBS CF10, or your Duran. Doing like functional end use parts, probably going to want to go with your engineering or high performance materials. For moderate demands or like harsh operating environments, where you're having to consider mechanical loads, operating environment, and production volume. So materials like that would be your nylon 12s, your Ultim 985s. You have kind of like a regulated or extreme application, like aerospace, medical. Probably want to go with your specialty or high performance materials. For certifications, extreme environments or specialized performances are essential, especially when you're looking for certifications, extreme temperatures, chemical resistance, or other specialized performance requirements. Some materials like your Ultims, your Antero, or your Vitrix AM200. Practical criteria for narrowing your material choice. Environment, what's your temperature range? Is it going to be exposed to chemicals like fuels, oils, solvents? Is it going to be in outdoors where it's going to be exposed to the sun, where you have to deal with UV? That's probably going to eliminate your general purpose materials quickly. What are your mechanical requirements? What's the load going to be on it? Is it going to be seeing any impact or fatigue from repeated use, or does it need any higher stiffness? Probably going to drive you towards your engineering or high performance. Is there any regulatory or special needs like FST, ESD requirements for electronics? It's going to be coming into contact with food, or does biocompatibility play a key role in it? Probably going to point to your specialty or high performance materials. Production volume and return on investment. Is it one-off or repeated use? Some of your higher categories may justify the higher cost for the higher end materials if it's going for production. Printer capabilities. Does your machine support high temp materials? Ensure compatibility to avoid limitations, especially when trying to run your Ultims or like even your nylon 12 CFs. There's some requirements for those. And then excellent thing that I found online is the Stratasys Material Wizard. You can filter by the properties and get ranked recommendations. If you're looking for a specific heat deflection temp or elongation, on this next slide, kind of an example of what that looks like, and then with the web address below. So you can move the toggle to the right or to the left to meet the specs that you're looking for, and then on the right-hand side of the screen, it'll kind of weed out what materials are left. Okay. Thank you for joining.